Hydrogen, the most abundant element in the universe, has long been hailed as a potential savior in our quest for clean, sustainable energy. Its appeal lies in its simplicity. When used as a fuel, hydrogen produces only water vapor as a byproduct, in stark contrast to the carbon dioxide emissions associated with fossil fuels. This clean-burning nature makes hydrogen an attractive option for a carbon-free future, particularly in industries and applications where electrification proves challenging. However, the promise of hydrogen as a clean energy source is complicated by a significant caveat. The production of hydrogen itself is often far from environmentally friendly. This dichotomy has led to the development of a colorful spectrum of hydrogen production methods, each with its own set of advantages and drawbacks. Understanding this rainbow of hydrogen is crucial as we navigate the complex landscape of future energy solutions. The most common form of hydrogen production today falls under the category of black, gray, or brown hydrogen, depending on the specific fossil fuel used in the process. This method, known as steam reforming, involves subjecting coal or natural gas to high-pressure steam. While effective in producing hydrogen, this process releases substantial amounts of carbon dioxide into the atmosphere. The scale of this issue is significant. Approximately 6% of the world's natural gas supply is dedicated to hydrogen production, resulting in annual carbon dioxide emissions equivalent to twice that of Australia. Given the environmental concerns associated with traditional hydrogen production, researchers and industry leaders have been exploring alternative methods. One of the most promising is green hydrogen, which represents a truly clean approach to hydrogen production. This method utilizes electrolysis, a process that splits water molecules into hydrogen and oxygen using electricity. The key to green hydrogen's environmental credentials lies in powering this electrolysis with renewable energy sources such as wind or solar power. Green hydrogen offers several advantages beyond its carbon-free production. It presents a potential solution to one of the main challenges of renewable energy: intermittency. By using excess renewable energy to produce hydrogen during peak production times, we could store energy for use when the sun isn't shining or the wind isn't blowing. This could help stabilize energy grids and make renewable energy more reliable. Additionally, green hydrogen could be used to decarbonize industries that are difficult to electrify directly, such as steel production or long-distance shipping. However, green hydrogen faces significant hurdles, primarily related to cost and scale. The electrolysis process requires substantial amounts of electricity, making green hydrogen currently more expensive than its fossil fuel-derived counterparts. There are also concerns about water usage, particularly in water-scarce regions. Despite these challenges, many experts believe that as renewable energy becomes cheaper and electrolysis technology improves, green hydrogen will become increasingly viable. In the interim, blue hydrogen has emerged as a potential bridge technology. Blue hydrogen is produced using the same steam reforming process as gray hydrogen, but with the addition of carbon capture and storage, CCS, technology. The idea is to trap the carbon dioxide produced during the process and store it underground, preventing it from entering the atmosphere. Proponents argue that blue hydrogen could allow for a faster transition away from gray hydrogen, utilizing existing infrastructure while significantly reducing emissions. However, the environmental benefits of blue hydrogen are a subject of debate among scientists and policymakers. Some researchers have raised concerns about the effectiveness of carbon capture technology and the potential for methane leaks in the natural gas supply chain. A controversial 2021 study suggested that blue hydrogen might only reduce greenhouse gas emissions by about 10% compared to gray hydrogen, and could potentially be worse than simply burning natural gas directly. However, other analyses have yielded more optimistic results, suggesting that with optimized processes and stricter methane controls, blue hydrogen could achieve significant emissions reductions compared to fossil fuels. The hydrogen color spectrum extends beyond these primary categories, with various niche production methods assigned their own hues. Pink, purple, or red hydrogen refers to hydrogen produced using nuclear energy for electrolysis. Turquoise hydrogen involves an alternative methane treatment that produces solid carbon instead of carbon dioxide. Yellow hydrogen specifically denotes hydrogen produced via solar-powered electrolysis, though it's often grouped with green hydrogen. White hydrogen refers to naturally occurring hydrogen deposits, though these are rare and not currently a significant source of hydrogen. As we consider the future of hydrogen in our energy mix, it's clear that there is no one-size-fits-all solution. The optimal approach will likely vary depending on regional resources, existing infrastructure, and specific applications. Green hydrogen represents the ideal long-term solution, offering truly clean energy production. However, the significant investments required in renewable energy infrastructure and electrolysis technology mean that it may take time to scale up to meet global demand. Blue hydrogen, despite its controversies, may play a role in the transition period, particularly in regions with existing natural gas infrastructure and favorable geology for carbon storage. However, its long-term viability will depend on advancements in carbon capture technology and careful management of methane emissions throughout the supply chain. The less common colors of hydrogen production may find niche applications or become more prominent as technologies evolve. For instance, nuclear-powered hydrogen production could be significant in countries with a strong nuclear energy sector, while turquoise hydrogen might be attractive in regions with a market for solid carbon byproducts. As we move forward, it's crucial to consider the entire life cycle of hydrogen production and use. This includes not just the emissions at the point of production, but also those associated with transportation, storage, and end-use applications. Additionally, the energy efficiency of hydrogen compared to direct electrification should be carefully evaluated for each potential application. The development of a hydrogen economy also requires significant infrastructure investments, including production facilities, transportation networks, and storage solutions. These challenges are substantial but not insurmountable, and many countries and companies are already making significant strides in hydrogen technology and infrastructure. In conclusion, the colorful world of hydrogen production reflects the complex challenge of transitioning to a cleaner energy future. While hydrogen offers immense potential as a clean fuel and energy storage medium, realizing this potential requires careful consideration of production methods, environmental impacts, and economic factors. As technology advances and costs decrease, we can expect the hydrogen rainbow to evolve, with greener shades likely becoming increasingly dominant. The path forward will require continued research, investment, and policy support to ensure that hydrogen fulfills its promise as a key component of a sustainable energy future.